Hey everyone, I said I was going to record a video working through a problem. I didn't get to it as soon as I wanted because I saw some headlines going on right now. But here it is. So on page 3 of this in class is what we're going to work on. So yours are backsided, but not page 1, not page 2, but on the top of page 3, I'm going to work through this problem on find the velocity of a 100-kilogram skier. Okay, that's when we're going to... Okay, so here's the problem. Find the velocity of a 100-kilogram skier at the bottom of the first hill if the skier is going 13 meters per second at the top of a second hill. How high is the second hill? Assume he starts at rest and the hill is frictionless. So the idea here is this is a two-location problem. So here's location 1, here's location 2. It works out nicely if we define the lowest point, which right there is the lowest point, to have a height of 0 meters, because then we can say that H1 is that 25 meters. And in this particular problem, we're trying to figure out what is that H2. Okay, so it's a two-location problem. We had started at the hill, top of the hill, bottom of the hill. Now, it's not asking about right here. It's talking about the top of the second hill. So we could really, there really are 3 locations, but we don't care about the bottom of the hill. So what we're really looking at is just where are we at that point. So, sorry, I just wanted to make sure I was recording. So the idea is this is a two-location problem. And because this is a two-location problem, we are going to go through, I'm going to make my pen a little smaller. We're going to go through and say, hey, that is not what I had intended. My apologies. We're going to go through and say, all right. So we are going to go through and say, that the work in okay, again, sorry about that. So we're going to go through and we're going to say that the work in plus the work done by friction is equal to our change in mechanical energy. Why? It's a two-location problem. This is our two-location problem. We have a location, two locations, therefore we got to use our two-location problem. When we go through, and it's on the sheet that I don't have easy access to with the screen recording, is for work in, we ask ourselves, is there an applied force and a distance? And the answer is no. There is no applied force. It's not being pushed down the hill. He's not pushing off with his skis. There is no work going in. And the fact that it says frictionless, we also have this idea that there is no work being done by friction. So we could say 0 is equal to ME2 minus ME1, because that's what delta ME stands for. It's the change in mechanical energy, ME2 minus ME1. Now, a little quick math and switching the terms around, we can say that ME1 is equal to ME2. This is a special type of two-location problem called conservation of mechanical energy, because my mechanical work in is 0 and my work done by friction is also 0. It's a special type of two-location problem. So, two-location problem, because it's a two-location problem, mechanical energy, we can go through and say, hey, it's conserved. How do we determine the mechanical energy at location 1? At location 1, well, mechanical energy is when we take our kinetic energy at location 1 and we add it to our gravitational potential energy at location 1, and we add that to our potential elastic energy at location number 1. And then we set that equal to our mechanical energy at location 2, which is equal to KE2, PEG2, and PEE2. Now, from there, we can go and we can ask ourselves those same questions, and whether we have kinetic energy, gravitational potential energy, elastic potential energy at each location. If he starts from, I should go back to my picture. I apologize. Let's go back to the picture. On our picture, we want to label V1s. We want to label V2s. We want to label H1s. We want to label H2s, right? And we already have this idea that we're looking for H2. So at the top of my hill, it says, assume that he starts at rest. My V1 is going to be 0. If this is my starting, my height of 0, then my H1, like I had said earlier, is going to be 25 meters. It says that if the skier is going 15 meters per second at the top of the second hill, that means that skier's V2 is 13 meters per second. That's my V2 value. Now, by having those identified is going to help us get kind of be able to cross some stuff out. So, at location 1, kinetic energy. Is the object moving? Does KE1, is the object moving? And the answer to that question is no. So because the object is not moving at location 1, there is no kinetic energy at location 1. Is there a height at location number 1? The answer to is there a height at location 1 is yes, there is a height at location 1. Therefore, we have to keep PEG1. For location 1, PEE1, is there a spring? And the answer is no, there is no spring. At location 2, now we're looking at kinetic energy. At location 2, is there a velocity? The answer is yes, there is a velocity. We have to keep KE2. Is there a height at location 2? The answer is yes. I don't know what it is, but yes, there is a height. Is there a spring? The answer is no. There is no spring found at location number 2. So now we can go through and we can break these equations apart. The equation from that formula sheet for PEG is M times G times H, and because we're talking about PEG1, we want to talk about H1. Everything else cancels out on the left-hand side. And that's equal to my kinetic energy at location 2, which is KE2, is 1/2 mv2 squared. And then we have to add, right, we have to add my PEG2, which is M times G times H2. Now, some of you might go through and say, hey, I have an M in every single term on both sides of my equation. Because I have an M in every single term on both sides of my equation, can't I cancel the mass out? And the answer is yes. If you say, are you sure? Then keep it. Don't cancel that number out. But if you're confident that you can cancel that term out, go ahead and cancel that term out. So filling in numbers, 9.8 times 25 is equal to 1/2 13 squared plus 9.8 times H2. Doing some math on our calculator, 9.8 times 25, 245. That's equal to 0.5 times 13 squared, 84.5, plus 9.8 times H2. Okay, now we are going through and we are going to go through and combine like terms. And the way we do that is we subtract 84.5 from both sides, 84.5. So 245 minus 84.5. On the right-hand side, we get 160.5 is equal to 9.8 times H2. Now we want to get H2 by itself. We go through, and in order to do that, we divide both sides by 9.8. We divide both sides by 9.8. So we take 160.5 divided by 9.8, and the height of that second hill is 16.38 meters for your final height. That's the answer to that problem. Again, frictionless, therefore we can get rid of this. There is no work in, so we can get rid of this. Because of that, we get this conservation of mechanical energy. That's how you do a two-location problem. If you have any further questions, please let me know.